You need to have AI end to end. You need to have AI in the understanding, the retrieval, the ranking. And this middle piece has been the missing piece. We've been so excited because we can now have AI in retrieval at scale, at cost, with low latency.
Welcome to How AI Happens, a podcast where experts explain their work at the cutting edge of artificial intelligence. You'll hear from AI researchers, data scientists, and machine learning engineers as they get technical about the most exciting developments in their field and the challenges they're facing along the way. I'm your host, Rob Stevenson, and we're about to learn how AI happens. Here with me today on How AI Happens is the Chief Technology Officer over at Algolia, Sean Mullaney. Sean, welcome to the podcast. How the heck are you today?
I'm doing great, Rob. Thank you so much for having me on.
Thrilled to have you. And I love that you are broadcasting in from your home office / fitness studio / wood-burning fireplace behind you. It's a unique setup you have.
Yeah, it's a rare sunny day in Ireland here, so I'm based in Dublin.
Well, don't hold your breath. I'm sure you'll get a cascade of rain at any moment here. That was my experience in Dublin, was beautiful sunshine, torrential rain, beautiful sunshine, just kind of on, off, on, off.
Yeah, they say if you don't like the weather, wait 5 minutes.
Yeah, just wait around. It'll change. Exactly that. I love Dublin, though. Loads of live music. The people there were so kind. You're lucky to get to live there full time. Yeah,
it's a fantastic city to live in.
And a fantastic city to build artificial intelligence in. So it happens. Seamless segue. You like how I did that?
Yeah.
We have so much to get into here, Sean. There is this new technology that you are debuting. You have all these great takes on keyword versus vector search. We're going to get into all that. First, though, let's learn a little bit more about you. Would you mind sharing with us about your background and how you wound up at Algolia?
Sure, yeah. So I joined Algolia as the Chief Technology Officer about 4.5 months ago. But before that, I've kind of had like a journey through the world of e-commerce and AI. So I was at Stripe, where I helped build up their European payments engineering team and got to see the kind of like late stage of the conversion funnel in e-commerce, where people are actually going to pay and helping to optimize that. Before that, I worked at a company called Zalando, which is Europe's largest fashion marketplace with about 50 million active customers. And I got to build a lot of incredible AI around search and discovery, particularly trying to bring AI into the search engine, personalization, recommendations, the browse experience, all the data infrastructure around that. So really the kind of like middle bit of the e-commerce experience. And then before that, I was at Google for 8 years and really got to understand how advertising works, a very data-driven business, understand how retailers could acquire customers and how they optimize that part of the e-commerce journey. And it was really at Google, actually, that I got exposed to AI really for the first time in production systems at scale. And when I joined Google, it was a mobile-first company, really focused on the Android operating system during that big wave of mobile explosion. But about halfway through, Google actually decided that they were going to become an AI-first company. And every engineer in the company got to go through a kind of AI boot camp, got to learn how to code in TensorFlow. And it really started my passion for AI and to see how AI could operate at a scale Google size, but also how it could affect e-commerce. Prior to that, I was an entrepreneur for 10 years. I had 3 startups just after the dot-com boom. And I'm very much an engineer. I've been programming since I was about 10 years old and absolutely love being in technology every minute since.
What was the first coding language you messed around with?
Oh, it was BASIC. I remember we got the first computer. It appeared when I was about 10 years old. And the very first thing I wanted to do was figure out how to write a text adventure game. So
fantastic.
I got the book out. Yeah, I got the book out, wrote out all the code, and then tried to figure out how to change it. And that kind of started everything.
So that was your print hello world, was like you enter into a foyer. Obvious exits are north, south, and east.
Yeah. So yeah, I've always been fascinated by video games as an on-ramp for kids into coding and software development.
Have you been able to keep that passion alive? Do you ever like on the side, code up a quick Tetris or something? I mean, what like I'm sure it's a lot more advanced now, the kind of thing that you could put together in Unity or a similar tool. But do you get to scratch that itch at all?
No, but I've been trying to work with my kids. I've got a 5, 7, and 10-year-old at home, and I'm trying to get them excited about programming, and video games is definitely the way that they get excited about computers.
Yeah. Is that like Roblox, or how would you facilitate that?
Yeah, there's some online courses that we use that really makes it fun and interesting for them, but have tried to hack around with a Super Mario game in JavaScript with my oldest one, but we're still working on it.
Hey, it's never too soon to expose kids to that kind of technology. And I love that it can kind of play along with video games. My parents were concerned that video games were rotting my brain. And now this generation is like, no, video games might give you a lucrative career someday. Let's make sure we steer into this.
Yeah, absolutely. Anything that gets them excited about computers and coding, I'm all for.
That's fantastic. So you are an engineer by trade. That is sort of your identity. I've spoken to other CTOs, and it's often like a stop on the path to becoming a CEO is like leading the technology department. But you are born and bred, so to speak, as a technologist, which is good to see.
Well, the great thing is every 10 years the entire technology industry changes. So there's never a shortage of new technology to learn, new things to build. I love building things, but I also love the commercial aspects. I love the product design piece of it, and I love working with customers and solving problems. So I think you kind of have to be excited about the full product development process, not just the engineering piece, in order to be successful as a CTO.
Yeah, of course, being able to see the full pipeline, I guess, or full cradle to grave approach.
Yeah, exactly.
So you, starting with Google and then onwards in your career, up until now, really, at Algolia, it sounds like search has kind of been a common throughput for you. When did you start to notice that there were some serious limitations to the ways that consumers experience search?
Sure. I mean, the original search engines back in the 90s were all based on the same keyword search technology that a lot of companies, particularly the e-commerce sector, are still using today. So it's been, 20 years. E-commerce has really taken off. Search engines have grown enormously, but really a lot of the base technology hasn't changed very much. When you shop online at the moment, you still have to think twice about, how do I tell the computer what I want? Humans have to kind of adapt to the fact that a lot of these websites are just databases with a nice user experience on top. And, as a human, you've got to adapt to the computer. You got to figure out exactly what keywords to put in. You got to figure out which filters to play with. And you got to figure out which categories to browse. So there's a lot that you have to do as a human to adapt to Google, to adapt to, your favorite website. And the technology itself really hasn't moved on a huge amount. There have been a little bit of AI added here, there, but it hasn't really been transformed in a way that feels natural and feels very human until very recently with these breakthroughs in large language models and ChatGPT.
It's such a good call out. I think a lot of people don't recognize that we sort of speak searchese in a way when you're entering a search query. For example, if I wanted to know where to go out in Dublin, I might say, hey, Sean, what's a good restaurant near you in Dublin that I should check out? But I wouldn't march up to you and go, restaurants Dublin, which is what I would do if I were trying to, to make a search query. Similarly, this is a well-tilled joke, a screenshot of someone's grandparents search Google and do you have any recommendations for restaurants I can go to? Please, thank you. Right? They speak almost in actual language, which is sweet. And it's funny. It's haha, grandma, come on. That's not how you talk to Google. But the contention is well, maybe it should be. It would be a lot easier for people. Surely people would be getting better search results if they could speak to a search engine the way they might speak to a person, right?
Yeah, absolutely. But it's not just the way that you ask the search engine the question. It's also the way the search engine responds. So, even today, 2023, we still get 100,000 blue links from Google where it's hey, here's some stuff that you might want to go and read. You still have to do all the work to go and read through all these web pages. Similarly, big e-commerce sites, present you 100 pages worth of products that you still have to go through and figure out which one's relevant for you or not. So, although we've had this great advancements in AI, the experience for customers hasn't really changed a lot, in the last 20 years.
Yeah. And the whole 100,000 blue links thing, it's a great way to put it because who needs 99,000,
exactly,
950 of those links, right? When's the last time anyone got past page 3 of Google results? I never get that far. But point taken, usually you make a search, the first few results are ads. And then it's usually someone who's a savvy marketer who's figured out how to rank well. And that's not necessarily that it's going to be super relevant to your need. It's just going to have, it's taking advantage of a system that's there to be taken advantage of.
This is why ChatGPT has been such a huge consumer phenomenon. It's 100 million users have adopted this in the last few months. We've never seen a product that has really taken the zeitgeist of the world by storm so quickly. And it's because it's the first time that users have really experienced that they can talk to a computer in a human way using their own natural language, and that the computer will respond in a very human way with natural language as well. It's not just giving you the 100,000 blue links and telling you to do the work. It's actually giving you the answers, and it's explaining stuff to you. And I think that's really elevated the expectation of consumers now, who are really going to expect this kind of technology to be available everywhere they go, whether that's Google or whether it's, a local e-commerce store that they want to buy a product from.
Right. And that difference is not merely the way it's presented to the consumer, right? We're speaking about keyword search versus other kinds of search, yes?
Yeah, absolutely. So the first thing that you have to think about in this kind of quantum leap is what we're doing with the language. So in a keyword search engine, you're taking the actual words and you're using that to match other words in the product or other words on the web page. So it's a very simple kind of algorithm. But what ChatGPT does is it uses these large language models, and these large language models are able to understand the concepts behind the words. And they're able to encode them in such a way that similar concepts are actually near each other in vector space. And what this unlocks is a very powerful way of matching things, which really understands the context and the concept that the user is looking for, regardless of whether the words match, right? And so this is going to unlock a very, very fundamentally different experience in the way we search.
How can you train results on context?
Yeah. So the first thing is that these large language models are trained on a huge corpus of human language. So kind of trillions of web pages and books and articles and tweets and all sorts of stuff from all around the internet. And what they've been able to do is really be able to map all of these kind of words, sentences, phrases into a vector space where we're able to really understand the nuance behind these concepts. And we've been able to do this for a while. I mean, the idea of embedding human language into vectors has been around for, almost a decade. The problem is that we've, first of all, never had models that have been this large. So the size of these models has increased by 100-fold. And with the size and with the increased size of the training data, they've actually become extraordinarily sophisticated. And they can now really, kind of mimic understanding human language in a way that has reached a quality threshold that humans actually feel that it can provide value for them. So the hard bit has not necessarily been the vector, understanding the vectors of the way forward. The hard bit is once you actually encode something with these vectors, how do you find out of all the web pages on the internet or all of the products in a huge e-commerce site, similar vectors? So the similar vector search problem has been the holy grail for the industry. And I'll tell you that the hard bits about vector search is firstly, with the explosion in size of models, these vectors have gotten huge. Right? So they're 500 floating point numbers, 1,000 floating point numbers. They're really big to store. And they're also really expensive to compare against each other, right? So computationally, you need a lot of GPUs to run these comparisons across a big index of web pages or products. And they're also really expensive to store because they're so big. So the industry has really been searching for a way to both store and search very large indexes of vectors at scale, at speed, and at a reasonable cost. And we've gotten very close. There are techniques like nearest neighbor, approximate nearest neighbor, which is considered the leading way to solve this problem at the moment. And there are companies like Pinecone and Weaviate and others who've been able to optimize this methodology, but it's still very expensive and slow. And this approach hasn't scaled to the level of a lot of production systems.
Can you speak a little bit more about the problem of matching vectors to one another?
Yeah. So when you match words together, right, you just match the characters. But when you match two vectors, what you're trying to figure out is how far apart in high dimensional space they are from each other. So, if you remember Euclidean geometry, you try to do the Pythagoras' theorem to figure out the distance between 2 points. Doing that in two-dimensional space, relatively easy. Doing it in 500 or 1,000 dimensional space requires a lot of computation. And so when you have to search through a very large index of vectors, which is your web page or your products that you're trying to match, with a query, which is also a vector, it ends up taking a lot of time, a lot of computation, and a lot of memory to be able to do that.
What solutions do you see to the problem of, it being expensive, lots of time? Is there Are there compression techniques? How would you go about making this more affordable, accessible, et cetera?
Yeah. So Algolia, we've been developing keyword search for the last 10 years. We're like the leader in this. We're actually the second biggest search engine in the world. We serve about 1.5 trillion queries for about 17,000 customers who are e-commerce and other websites around the world. And we've been on the search to solve this problem for many years now. And we've known, just like everyone else in the industry, vector search is the future in terms of human language understanding. But because we operate at such high scale with customers in the enterprise space, we knew that we couldn't really introduce a product until we solved this. So we're very excited. We just actually have launched a beta program with a technique we call hashing. And the idea is that if you can compress vectors using another AI algorithm called a hashing algorithm, you have to compress them in a very specific way. So we're able to retain pretty much 100% of the relevance and information of the original vector, but it's in 10 times less space. So it's extremely compressed in terms of the size. But the other incredibly important thing that we train the algorithm to do is to make sure that we can actually compare the similarity between these hashes that we created in extremely fast computational time. So the way that we're actually able to do and solve this vector problem is through these new hash data structures. So we're able to scale up to the trillion query level and to customers who are doing hundreds and thousands of queries per second on their websites, whilst using this very powerful vector technology through the compression mechanism and the similarity that's built into that compression mechanism.
Got it. So the searches that are being made by Algolia users at the enterprise level, what exactly are they searching for? They're searching through their own company's private data. What is the nature of what they're looking for?
Yeah, so we have about 17,000 companies who we power the search on their website, the search and discovery experience, including browse, including recommendations. Companies you'd know like Under Armour, Stripe, PetSmart, Walgreens, Sony, a lot of big customers. About 6,000 of those are e-commerce retailers. And so what we found is that with a lot of these let's take e-commerce, for example, there's a kind of a head of small queries that represent most of the volume, right? This might be people going to a fashion site, searching for red shoes or something relatively straightforward. And, keyword matching works pretty well for that, particularly when you have a good product catalog. But, about 70% of the queries on these websites are actually somewhere in the middle or long tail queries where, users very unique and maybe a one-off query that's never existed before. But it's customers who have a lot more detail that they want in their answer, or they're trying to solve a problem. So I'll give you a couple of examples where keyword search doesn't work as well, but vector search or neural search, as our product is called, works extremely well. So a lot of customers will turn up to let's say a pharmacy or a healthcare website like Walgreens, and they'll say something like they want to solve a problem. So maybe their baby's crying, and they'll type in baby crying, and what they really want to see is colic medicine, or they'll describe symptoms to something, and they really want to understand what medicine is available for those symptoms. Or they'll say something like, I want to get moisture out of the air, and what they really want is a dehumidifier, right? But they don't know the exact term for the item. They just know the problem they're trying to solve.
Yeah. And if you Google baby crying right now, I bet you the first result is a link to a YouTube video of 90 seconds of crying baby, right?
Yeah, absolutely. And then there's there are ambiguous keywords. So a good example I always use is the difference between chocolate milk and milk chocolate, right? Exact same words, but two very different products.
Yeah, good one.
The other one that I thought was great was when we look at hair growth cream. So someone's obviously looking for some cream to help their hair grow. And the products that get returned on most websites are products that are actually cream for someone with a lot of hair. So they get the opposite of what they're looking for. The other incredible thing we've seen is these language models have been trained on such a large corpus of information around the internet that they've understood a lot of things like brands, for example. So a lot of people, would go to a website, let's say a fashion website, and they would put in a brand they want. So let's say you're looking for, UGG boots. They would search for UGG, and maybe the retailer doesn't sell UGG boots. So most of the time they get a no results link. But these language models understand that UGG is known for its furry boots. And so it will actually return other furry boots from other brands for you because it really understands the concepts behind the products that these brands are selling.
Okay,
So
it's a little bit like on Netflix. If you search for a movie, they don't have it. They don't just say no results found. They give you like 90 other movies that are kind of like it.
Yeah, absolutely. So like if you search for North Face and there's none of that brand, they'll return other outdoor jackets for you. And this is really, really important for a lot of e-commerce sites who have a like limited brand selection. The other one that I find interesting is like expert domains, right? Where people don't know the terms. Like when I worked at Zalando, fashion has a lot of very specific fashionista type terms. And if you don't know the term, you can't actually get any good search results. And the one that I always thought was very, very interesting was one called Chelsea boots. I had no idea what a Chelsea boot was. But it turns out lots of people don't know what a Chelsea boot is, and they search for like kind of brown or black shoes with no laces and a little pocket on the side, which is basically what a Chelsea boot is. But they don't know what the word is, so they're kind of just describe it in a way that they're hoping to find out what it is. So you can imagine, you know, electronics, for example, people might not know all the technical terminology, or in fashion, they don't know the fashionista type terms. And it just turns out all of this adds up to a lot, right? So about 70% of the searches that happen on these websites are folks who are entering something that's not like just a standard kind of keyword.
Okay, that makes sense. In this example, though, I use like search baby crying. You want actual colic medicine, but on Google, you might get a video of a baby crying. In that example, is vector search more useful in the colic medicine example because you can assume buying intent on the part of the searcher?
Yeah, it's a good question. I think the context matters a lot. So what we do with a lot of the websites is we take the click and conversion events that happen from the website. So we observe every query. We then see where users click, and then we observe where users are kind of checking out and buying things. And what we can actually do is we can use all of that event data, analytics data, to fine tune and train these large language models. So we take a base model and then we fine tune it to a specific website using their specific customer interactions. And it really, really increases the relevance and recall of the search results. And so we have a model for every single one of our customers. And those models are really fine tuned and updated all the time using live data so that we can get that context and we can kind of like see the feedback that's coming from customers.
Thanks for sharing that about the searches going on Algolia's products. I thought that was important to clear up. Before we got too deep in the weeds with the compression technology, I would love to spend a little bit more time there. Can you kind of share just how that works, how that technology was wrought?
Yeah. One of the ways that people have been trying to solve this for a while is using this nearest neighbors algorithm. And you can see the major vector search engines in the market, like the Pinecones, Weaviates, even Google's kind of vector search engine uses this nearest neighbors approach. And folks have been trying to optimize this nearest neighbors algorithm for a long time. And it requires using a very specific data structure where these vectors have to be organized into like a tree or a graph or a hierarchy so that you can search through them more efficiently. So a lot of the research has been in the optimization of this like tree data structure and optimization of how the vectors are stored and searched and rebalanced in this tree data structure. And it's kind of been like, you know, the industry's gotten stuck over here on this data structure about trees and nearest neighbors. And so we were so excited to say, let's actually change the entire way in which we want to solve this problem. Instead of trying to optimize over here around nearest neighbors and trees, and let's actually look at compression. And I'm pretty excited. I think, you know, we're the only company in the world that has been able to get a breakthrough in the scale, the speed, and the cost of vector search like this. And we're very shortly going to be announcing both the commercial product being made available, as well as some interesting benchmarks and data around the kind of breakthrough so people can see just how much better it is than the other existing vector search approaches.
So if the existing paradigm was the tree, like to conceptualize it as a tree, how would you conceptualize the compressed version? Is it like a tree where the leaves are all much closer together, or is there a better way to maybe imagine it in my brain?
Yeah, I mean, really what you're trying to do is you're trying to take this huge vector space and compress it down into a much smaller space, but where all of the vectors that are conceptually close to each other in the high dimensions are also kind of like numerically close to each other in the hash, which means that you can use a kind of binary comparison as you're going up and down the hash. And it took, to be honest, several years worth of experimentation to figure out how to do this hashing, how to train the algorithms, and how to use data to make the hashes work. It's been a lot of research, a lot of experimentation. But in essence, it is a compression technology, and it is one where it requires rethinking both the data structures as well as the representation of the vectors. But what we're excited about is that these hashes can work in a traditional database environment. The nearest neighbor structures really require a different type of database structure, a different type of data structure to search through, which means, if you've got your data right now in a database, you have to replicate it and you got to hand it over to, someone like a Pinecone, and it's got to be stored separately in their very specific vector database. And so there's all sorts of really interesting and important implications about this hashing technology. And I'm pretty excited. We're going to be sharing a lot more for developers and for the impact on e-commerce in specific over the coming weeks.
I'll definitely put some links in the show notes so people can sink their teeth into some of the technical stuff if they care to. Quickly, or before we move on, I did want to ask also, you mentioned the binary comparison. Is that like comparing the hash like relevant, not relevant? What is the binary there?
Yeah, so just like the way nearest neighbors try to find similarities between the distance in high dimensional space between two vectors, we're just figuring out a different way to do similarity in vector space, but just in a compressed format. We figured out ways to make it much faster to search through.
Okay. And then when you say high dimensional space, do you mean the distance between two possibly relevant search terms or search ideas, or is it high dimension more of like the indicator of relevance?
Yeah, so you can think about a vector. Let's say it's a 1,000-dimension vector, okay? And what you do is you take all your products or all your web pages and you reduce them down into a 1,000-dimension vector. And then you take a query coming from a user and you reduce it down to a 1,000-dimension vector. And then your algorithm is really just trying to find the distance between your query vector and all of the web page and product vectors. And, these tree structures help to kind of make that search process a bit faster. But you still have to compare 1,000 floating point number vector with another 1,000 floating point vector number to figure out the distance between them in 1,000-dimension space.
Okay, got it. Thanks for clearing that up for me. I'm no AI expert, so I wanted to just to stop you to do some quick vocabulary there. Okay, so that kind of outlines how the search would go about finding possible matches. However, it's not going to just find one possible match. In Google's case, it might find 100,000.
Yeah.
And presumably in Algolia's case, it's finding fewer, but more than one. And now the goal becomes, all right, how do we serve these up? How do we rank these, perhaps in order of relevance to the searcher? How are you deploying AI in the retrieval set when it comes to ranking results?
Yeah, as I talked about earlier, this using vectors in the retrieval phase has been like the holy grail. But what it also unlocks is it unlocks the end-to-end AI when it comes to processing search queries. So, a query goes through 3 phases when it comes to producing search results. The first phase is understanding the query itself. So that's the text to vector transformation. But it's also trying to identify, are there words in here that indicate this is part of a category of products? Like, is this a TV product, or is this chocolate milk is a milk product, milk chocolate is a confectionery product, right? So there's actually some clever AI that you can do at the start. Traditionally, people would use synonyms as a way to make up for the lack of specificity of keywords. So some people have said AI search, and when they really mean they're just bringing synonyms out of a dictionary using some AI and stuffing them into the keyword retrieval phase. So that's the first thing, is the query understanding, and there's a lot of AI there. The second phase is retrieval. We talked about, how we use vectors in retrieval. But the third phase is actually where probably most of the AI has been focused in search over the past few years, which is once you've retrieved the top 1,000 results out of the catalog that could contain hundreds of thousands of different products, for example, you can actually do a lot of powerful re-ranking with 1,000 candidates that you couldn't do in the whole result set, 100,000, a million, that kind of thing. You couldn't re-rank all of those. So what it turns out is that we now have a keyword score, right, from the keyword engine, and we've got a neural score as well, or a vector score. And what we can do in this ranking phase is actually, we can get a lot more power and relevance by using AI. We use a learn to rank algorithm, whereby it's a machine learning algorithm that's optimized to place the order of items in the correct order. It's a very specific type of machine learning algorithm. But what we can do is we can use this learn to rank algorithm and take all sorts of input. So we take keyword scores, we take this vector search score, we can take personalization signals, what we know about the customer. We can take popularity scores because we understand what people have clicked on in the past. So we can understand how successful it's been in the past. We can even take stuff like business metrics, how much margin you'll make on the product, that kind of thing. And these learn to rank algorithms figure out the precise order of the items so that you can increase the relevancy and hopefully get a customer engaging with a product or a web page far higher in the results set. Because we know that that first row of items or first set of links on Google always get the most clicks. So if you can really make sure that the most relevant thing that's going to engage the user is up at that top row or in those first few links, you're going to get like way higher performance. So what I'm trying to say is that this all builds together. Like you need to have AI end to end. You need to have AI in the understanding, the retrieval, the ranking. And this middle piece has been the missing piece. And we've been so excited because we can now have AI in retrieval, right? At scale, at cost, with low latency. And it means that the whole AI end-to-end is seeing huge increase in performance and huge increase in the relevancy for shoppers and for all sorts of users across our customer base.
It is exciting. It sounds like with retrieval, you're basically weighting the search results based on a ton of different factors. So one example being like, oh, the profit margin for the e-commerce vendor. Now, the vendor might be like, oh, we'll put that one at the top, right? We make the most money off of it. Let's rank that. But you would counter, is it the most relevant to the person's search? They're not going to buy it. Doesn't matter how high the margin is, right? It's not relevant. So it's just one factor. It's many factors in helping someone get the results they're looking for.
Yeah, exactly. And the re-ranking phase, the AI can be very sophisticated and it can balance all these different inputs to really figure out how it can serve the best result for a user. By using vectors at retrieval, we give this re-ranker much better candidates, right? And like, example is if like you're playing poker, you can only play poker with the cards you're dealt, right? If you don't have an ace, you can't have a royal flush, right? And it's just like that with re-ranking. It can only do its job as well as the candidates that it receives from the retrieval phase.
So I can see why this would be fantastically useful for someone like Sony, right? Under Armour, companies like that. At what point do you expect this will make its way to your average consumer who's just using search to find things in their life and to answer questions for themselves outside of a buying experience?
Yeah. So as I mentioned before, we've got 17,000 websites that are powered by our technology and 1.5 trillion search requests across those. And I think it's something like 1 in 6 users will use Algolia or one of the websites powered by us. So I'm pretty excited about how far this technology is going to reach once we roll it out to our existing customers. And we've seen some incredible results. So, as I mentioned, I've been working in e-commerce a long time. And, we've have beta users now using the product that are seeing multiple double digits increases in revenue, in conversions, in engagement, seeing like 60, 70, 80% drop in no result rates. These are numbers that are just, off the charts, like for companies. I mean, imagine being a retailer, for example, an e-commerce retailer, and being able to like increase your sales by double digits by turning something like this on. And that's a real testament to how much customers value being understood. When you can show them that you can understand them and you can show them that you can help them look for those weird and crazy things that they can't tell you with keywords, they'll reward you by buying more products with you and by using your product more. So we're pretty excited that customers are going to be able to, shoppers and web users are going to be able to have a pretty much more human and natural experience as they engage with websites.
I'm excited too, because search is a huge thorn in my side. So I wish more and more companies would be adding Algolia to their stack because it would definitely make my life easier. Sean, have surged past optimal podcast length here, but it's only because I've had such a great time chatting with you. So thank you for being here with me and sharing all of your expertise. I've really had a blast in this episode.
Great, Rob. It's been wonderful to join you. Thank you so much for the chat.
How AI Happens is brought to you by Sama. Sama provides accurate data for ambitious AI. Specializing in image, video, and sensor data annotation and validation for machine learning algorithms in industries such as transportation, retail, e-commerce, media, medtech, robotics, and agriculture. For more information, head to sama.com.